So good evening, everybody, and welcome to yet another podcast from Physics for Students. And just to let you know that we are meeting today on a historic day. Today's date is 30th of June 2024, and 30th of June 1905, on that same date in the year 1905, 26-year-old Albert Einstein formulated the two postulates of special relativity on today's date. The postulate says that the principle of relativity, the laws of physics will be the same in all inertial frames of reference and the constancy of speed of light. We all know 10 years after that, Einstein expanded on his magnum opus, what is called Einstein's general theory of relativity, and it forever changed our perception of looking at the universe, fabric, space, time, everything got different. So, on this historic day, I am feeling very honored to welcome Dr. Geetanjali Sethi to our podcast today. With a PhD in theoretical cosmology from the University of Delhi, her illustrious academic journey includes an MSc and BSc in physics from St. Stephen's College. Recently awarded the Indian Council for UN Relations for Excellence in Academia, Dr. Sethi's groundbreaking work on radio astronomy and theoretical cosmology, particularly her research on pulsar distribution and energy models, is truly inspiring. Her innovative efforts in building affordable horn antennas and contributing to the nationwide interferometer array are transforming the field of radio astronomy. I heartily welcome Dr. Geetanjali Sethi for giving her time. Dr. Sethi, very warm welcome to today's podcast.
Thank you, Shonak sir. Thank you so much. It's a pleasure to be here. It's an honor that you gave me this opportunity.
It is my honor to have you. Quick some comments. Nadeem Iqbal, welcome Professor Shonak and Dr. Sethi. Looking forward to learn from your knowledge. Karan Nalawat, a very old subscriber, and just like my son, good evening. Rudrasi, also equally great, is telling namaskar. And Dhanvil Kapadia, physics, is telling good evening. And Rohit Gupta is also telling welcome, ma'am. So we
Good
already
evening
got
to
a
all.
lot of, and Rohit Gupta also, welcome, sir. Okay. So just to set the stage on, Dr. Geetanjali would be showing a presentation which would set the scene on, and that would be our journey into cosmology. With that, once we complete Dr. Sethi's presentation, all the subscribers are all welcome to participate and ask questions. I'm very happy that on 30th of June, being a historic day when special relativity was published by Albert Einstein, we are meeting with a similar kind of a person, Dr. Geetanjali Sethi, to speak on podcast and cosmology. I will put the screen on and hand it over to Dr. Sethi with her presentation.
Sir, those were real great words. Thank you so much. Yeah, but it's a pleasure talking to students always.
Okay, just a quick note. Somebody from Jamaica, Renaldo Jones, is telling good evening from Jamaica. So, Renaldo, very good evening from Jamaica. Pavan Gaonkar has already got a question, but we will come to that. Pavan, just be there until Dr. Sethi has got a plan. We will listen to that.
Right. Yeah. Okay. Thank you, Shonak sir. I'll take over from here. Right. So thank you everybody for being here and good evening to all. I'm going to talk about very basic idea. I'm going to give you a very brief introduction to cosmology. Cosmology is a very wide subject. It is very difficult to talk about what all is going on, what all has happened historically, and what all we can look forward to in an hour or so. But so my idea here is not to teach you today, but to get you interested into doing some maybe some cosmology or general relativity. Okay, so this is going to be the brief plan of my talk. I'm going to start with some very basic introduction to observations that have been made, how observations have led to theory, and how theory now tries to explain what we observe. Right. So, okay, so we'll start with one of the very famous. I mean, this is one picture that all of you, those who are here, must have seen at one or the other places, or even if you just Google cosmology, expansion of universe, expanding universe, anything, any such word, this is probably one of the first images that shows up on your screen. So this figure actually represents the expansion history of the universe over last 13.77 billion years. I mean, it's the timeline that shows some very important milestones, different milestones in the expansion history of the universe. If we start from here, is where one can think of the beginning of the universe, and as we go along the x-axis is where as the time elapses, right? So we can see that as time elapses, this is where the first stars at about 400 billion years after what we call as the big bang is when the first stars appeared. Then we have development of galaxies and planets following that, and this is where we are today, is where we have dark energy dominated accelerated expansion of our universe. It's one of the most interesting observations, and that's what we'll be trying to explain through our theory, and that's what we see from the observations, right? So with this image we set a note on what exactly is cosmology. That's the first question arises whenever you start talking about something. So what exactly is cosmology? Cosmology is the study of universe as a whole at largest scales. When I say largest scales, what do we mean by largest scales? What scales are we talking about here? What length scales are we talking about that we call as largest scales? Not only that, cosmology is also the study of what are the components of the universe, how they behave with time, what does the universe contain, and to explain the dynamics of the universe, which we'll see is connected to what the universe contains. Okay, so when we talk about scales, distance scales, scales or distance scales in cosmology, not only in cosmology, in physics in general, are a very important concept, right? So what are the smallest scales that one can associate with cosmology is something which is completely unimaginable. So when we look at the smallest scales that we come across in astronomy astrophysics, not even cosmology, in astronomy astrophysics, the smallest scale that we think of is the distance between earth and sun, is what we call as one astronomical unit, which is already some 1.5. If you, I don't know whether you can see the figure is big enough or not, which is roughly 1.5 into 10 raised to the power 5 kilometers. It's already something which is unimaginable. We can't even think of what it is. Then the next length scale that we come across in astronomy astrophysics is that our sun and earth are a part of our solar system. So extent of our solar system is the next scale, and our solar system is then, so this is roughly what we call as 1 parsec, which is already 10 raised to the power 13 kilometers. Our, and the next scale is the scale at which we talk about our galaxy, which is another 10 raised to the power 3 times the size of our solar system, which we call as what, which is 1 kiloparsec, right? And then comes these, that galaxies are parts of clusters, superclusters, which are at the scales of 1 megaparsec, which is another 10 raised to power 3 kiloparsec. So you can see that the kind of scales that we are talking about in astronomy astrophysics are completely unimaginable, and yet we've not reached cosmology. This is not where we start. This is still in the domain of astronomy astrophysics. We're far away from cosmology. Beyond galaxies, beyond the clusters is where the cosmic scales starts. So cosmology, we talk about cosmology when we are talking about scales of the order of 100 to 1000 megaparsecs. That is another 10 raised to power 3 times larger than the scale of clusters or superclusters. So you can very well think that at such scales, even individual galaxies do not retain their structure. You don't talk about individual galaxies anymore, but you talk about what universe looks like at these scales. So this is an image which is going to give us an idea about what actually are we dealing with, what are we actually looking at when we are talking about cosmology, right? Okay, so what is this? This is a slice from a very famous, what is known as the 2DF galaxy redshift survey, where the sky was mapped to study galaxy redshifts over very large cosmic scales, right? Now this figure shows two-dimensional size of a 3D galaxy survey, and you can imagine that, let's say we are sitting here at the center of this image, and these are radial distances away from us. When I look at this axis, zero point 0.05, zero point 0.1, this is right now in terms of redshifts, but this is, if I talk in terms of distances, this is some 300, 400 megaparsecs, right? So as I just told you, one parsec was a scale of a cluster, so 300, 400 megaparsecs, right? So this image, if I look at this image, then here each individual point on this image is a galaxy, right? So you can see, that's what I said, that even individual galaxies do not retain their structure. This is an angular scale, so this is the third dimension has been collapsed, and we are looking at a two-dimensional projection of a three-dimensional survey. So all these points here are galaxies. So you can see at these scales, the structure is not random, right? The galaxies have a very intricate, they form a very intricate structure. They form filaments, nodes, and there are these regions where where there's nothing, right? There are actually areas where which are whiter. So these are areas which are denser, where you have large number of galaxies. They form what you call as nodes. The points of over densities is what you call as nodes, and then these are under densities, regions where no galaxies are seen. These are called voids. These void itself, if I translate this into in terms of distance, these are some 10 to 40, 40 to 50 megaparsec in length, right? So you see that there's a very definite kind of structure, but you don't see individual galaxies. By the way, these voids are regions where you don't see galaxies, not because your telescope or your survey is not um, sensitive enough to see, but these are actually regions of under density. Because your survey is actually mapping sky at very large distances. It's very sensitive to see up to hundreds of megaparsecs. So these are 40 to 50 megaparsecs regions. So these are actually regions where you have missing, you don't have anything. These are called voids. This as I said, is something which is at a scale of 300 to 400 megaparsec. If I extend this up to, let's say, some gigaparsecs, maybe 2 to 3 gigaparsec, we'll realize that the universe would still look the same. That is, we'll still see these filamentary structures, we'll still see these filaments, we'll still see these nodes and voids. So it's going to retain its structure, its form, even at such large distances, right? What happens if we go further ahead? If we try to map the whole sky, this is what the whole, if I look at the whole sky as very large, at very, very extremely large scales. I mean, by the way, this is still what we call as closer to us in terms of cosmology, right? In cosmology, these distances are still distances. What we say, that is gigaparsecs, is still what we say is closer to us. So these are scales much, much. This is an image at scales much, much larger than, and you can see this is a completely, so if I actually go by the fact that the color here represents uniformity or density or structure in terms of representing, being represented as color, you can see it's completely uniform, right? So this is nothing but what we call as the cosmic microwave background radiation. So universe is said to have a very uniform temperature radiation bath, right? This bath is at a temperature of 2.725 degree Kelvin, and this is what is famously known as the cosmic microwave background radiation. And you can see this number. You look at the accuracy to which this number is known. This uniformity exists at a scale of 10 raised to power minus 3 degree Kelvin. That is, if I look at any direction, if I go observe a patch in the sky at any point along any direction, and I am able to measure temperature at scales of 10 raised to power minus 3, I'll still measure the temperature to be same everywhere around us at, and that would be 2.725 degree Kelvin. So
Just
this is
one question, Doctor. Is
sure.
that this color, this green color, I mean to say, how is it portrayed on this? Is it
Nothing.
something?
So the color has no significance. I mean,
Okay.
it's just, as I said, the color is a representation of uniformity. You could show it with blue. You will see some images show it as blue, or any other color. It's just green you should go by the fact that this is green everywhere. That's it, right? So that means everywhere, if green would represent 2.725 degree Kelvin, then it's green everywhere. That's what we understand. And
That is what we call it is homogeneous and isotropic.
yes, yes, that's what we are going. That's what is going to form the very basis of our remaining theoretical idea about cosmology, right? Okay, so what I was saying was that this is actually one of the most remarkable observations in cosmology and a great achievement in terms of precision cosmology. I mean, the kind of precisions now we talk about in cosmology, even at, I mean, one can think of length scales that we are dealing with experiments that cannot be repeated. There are no, it's not like your lab where you can perform your experiment again and again and again, right? Still we have an accuracy of the order of 10 raised to power minus 3 degree Kelvin. In fact, you will see that this is one of the predictions of the standard model, and that's what actually is a great supporting argument in for the standard model of cosmology, the lambda CDM model, right? But this graph, this figure here is a observation that has been made, right? Okay, so so this is what the last two images show us, what observations tell us. So observations tell us that our universe at very, very large scales, as Shaunak sir just said, rightly said, is very homogeneous and isotropic, right? In fact, this is one of the most fundamental assumptions in cosmology, that our universe is indeed homogeneous and isotropic when smoothed over very large scales greater than hundreds of megaparsecs. And this has been validated by what we've just seen in the last two images. So, what do we understand by isotropy, or what do we understand by homogeneity? So, I would like to tell you about this because this is going to form the basis for the framework of theoretical cosmology, or the idea that we are going to build on. So, isotropy is the universe looks the same in all directions. That is, if I look at any direction, I will see the universe to be exactly same. And we've seen that we have a direct evidence for this isotropy from the smoothness of temperature in cosmic microwave background, and that the fact that the universe is very homogeneous is there is homogeneity in the universe. That is, if I pick up, I go to any point and I see that point, any point, it's exactly the same. It's very difficult to test this directly, but if I go back and look at the 2DF galaxy survey, what I mean by homogeneity is that if I, let's say I have a sphere of radius a few megaparsecs, right? And I place it at different parts in this image, and I count the number of galaxies that I will have in that region, that would almost remain same. That's what I understand by homogeneity. So if I move that sphere all over this image, keeping the size of the sphere same and counting the number of galaxies, that would remain same. That's what I understand by homogeneity. So isotropy and homogeneity are two extremely important assumptions, are the basis of my of cosmology. And then if I say that I or we do not have a special place in the universe, and if things are isotropic with respect to me, they have to be isotropic with respect to every other point in the universe, right? This is what is known as the Copernican principle, right? So that means that I have no advantage of my location where I am, right? If I go to any other place and still look around myself, I would still see universe to be isotropic, right? So this is what I known as what is known as global isotropy. And there is a theorem in physics which tells you that if you have global isotropy, that would automatically imply homogeneity. That is, if something is isotropic at about every point, then it has to be homogeneous. And these things, these two things put together is what is known as the cosmological principle. So cosmological principle is what forms the basis of the theory of cosmology, the theory of universe, how we start writing, how we start building the mathematical framework to explain the dynamics of our universe. That's what is known as the cosmological principle. Okay, so we go ahead. We've kind of set up our basic assumptions. But before we start building our mathematical framework, there's a very important um, observation that one cannot ignore when one talks about cosmology. Was made by this, uh, observation was made by Hubble in the year 1929, when he was actually measuring distances to distant galaxies using what are known as Cepheid variables. So Cepheid variables are stars which have variable where the I mean they have variable intensities, luminosity. Their luminosity changes with time, and there's a fixed time period, and so can be related to the intrinsic property and can be used to measure distances to these Cepheid variables. So if you observe Cepheid variables in galaxies, measure distances to them, you can measure distance to the galaxy. Measuring distances is an extremely important thing in cosmology, as you will realize as we progress. So, Hubble in year 1929 studied these Cepheid variables and measured distances to distant galaxies. He not only measured distances to these distant galaxies, he also observed the spectral lines coming from these Cepheid variables from these sources. And he observed that the observed wavelength, the wavelength that the wavelength of the light emitted or the spectral lines emitted from these sources was shifted from what was the actual wavelength at which it was emitted. So how do we know that this is shifted? Because we know we have a standard spectrum for all atoms and molecules, and if we compare that standard spectrum that we have in the lab with what we observe in astronomy astrophysics, is how we normally measure the shift in the spectrum. That is, we see that whether the line is blue shifted or red shifted, that is shifted towards the blue part of the spectrum or red part of the spectrum. And then he defined this quantity called redshift, which was nothing but the ratio of the wavelength that was observed and the actual wavelength that was emitted by these Cepheid variables. So if you look at the way the relation is defined, z less than 0 would imply blue shift. But what he observed when he actually measured this ratio, he observed that all distant galaxies were redshifted. So what does this mean? And he plotted this redshift because he was measuring distances also, and he was observing redshift. He plotted this relationship between this he plotted a graph between the redshift and the observed distance, and he found that there existed a linear relationship between the redshift of the galaxy and the distance of the galaxy in terms of the Cepheid variables. Right now, if you go back to your basic knowledge of physics from Doppler shift, you know that we can relate the blue shift or the red shift to the velocity of the source, right? And if I look at that expression, I'm sure everybody must have seen this expression, those who have a background in physics, how velocity of the source is related to the blue shift or the red shift of the observed light is given by this relation, and this relation reduces to 1 plus v by c in the limit if the velocity of the source is much smaller than c, which is velocity of light. So what do
So
we
you
see?
were considering this equation on the non-relativistic part. If we consider the
Yes.
relativistic Lorentz transformation, it would be something different.
Yeah, right. So this
Okay.
is still the within
Right.
the non-relativistic regime, right? But though, I mean, now we know that we know that this redshift that we observe in cosmology has nothing to do with this. It's actually because of the expansion of the. That's why everything is redshifted, is because it's because of the expansion of the universe. Okay, so if we go back, we see that z can be directly related to v, and if we put these two expressions together, that is z is equal to kr, and writing z in terms of v by c, I can write that equation as v is equal to, forget about what is h naught. H naught, if you go back and just do the mathematics, you can see that h naught is nothing but some constant ck and multiplied by r. I just said forget about H naught. H naught is not something that you can actually forget about. It's one of the most important quantities in cosmology, is now what is known as the Hubble's constant. In fact, this is value of what we now realize Hubble's constant is not really a constant, it's Hubble parameter. It actually is a function of redshift, and Hubble's constant is the value of the Hubble parameter today at uh, today's epoch. But what is more important to see here is that V, what is this V? If you go back, this V was the velocity of the galaxies, and R was the distance to the galaxy. So what you see is that V is equal to H naught R. And it's a very important relation. Why? But because what it tells us that larger the R is, that is, farther a galaxy is, faster it is moving. And moving in what way? As we just saw, all distant galaxies show redshift. So that means they are moving away. So this tells you something extremely important, is that all distant galaxies are moving away from us. The farther the galaxy is, it's moving away from us at a greater velocity. This is what is known as Hubble's law. But in fact, Lemaitre, another cosmologist, had actually, so this was 1929, had actually published a paper in 1927, 2 years before Hubble, and found the value of this constant, what was now later on known as Hubble's constant. So this law is not now known as Hubble's law only, it's known as actually Hubble's Lemaitre law. So it's a very important observation one must understand, because this is something you observe, is that all distant galaxies are moving away from us. And these are actual data points that have been taken. This is real observation, and we can see the linear fit. This is distance in parsec. Distance to these points are distant galaxies. So this is their distance from us, and this is their observed velocity. So you can actually see that the velocity of distant galaxies is has a linear relationship with the distance. And if you look at the slope, measure the slope of this graph, you can actually estimate the value of Hubble's constant, right? Okay, so with all this established, I think it's time that we can now build upon a framework to explain the dynamics of our universe, right? And write down some mathematical equations to explain the expansion of the universe. But let me tell you, it's not that simple. Why? Because to write the to build a mathematical framework, to write those equations, you require knowledge of general relativity. Right? That's where general relativity becomes very important, because that's the mathematical language of cosmology, right? So there's a so
Just to
when
interfere, I think we have already come to that point. Pawan was asking that question. Good
yeah,
evening. How much of general theory of relativity plays? I mean, it should play a role in cosmology. I think we are actually, Dr.
going to
Professor.
answer his question.
Yes, you are. So
Yeah,
Pawan, you can now understand that we are going to answer this question.
yeah. Right. So, as I said, every time, and that's true even when you study mechanics in school, is that every time you want to study dynamics, the first thing that you need to measure is the distance, right? You always want to measure distance and then see how distance changes. And that's what give you dynamics of objects. And that's how we will approach even when we study dynamics of the universe. So, but there's an important thing that you need to keep in mind, is that appearance of objects in at cosmological distances. We know now what we mean by cosmological distances. The length scales we've already discussed is affected by the curvature of the space-time through which light travels on its way to Earth. This is where general relativity comes in. The most complete description of geometrical properties of the universe is provided by Einstein's general theory of relativity. And in GR, we define a fundamental quantity, which is called the metric, which describes the geometry of the space-time. So if I want to describe the geometry of the space-time, measure distances, and one way to measure distances always in physics is you send a light signal, you know the speed of light, you measure the time it has taken, and you'll be able to measure the distance it has traveled. So that's the idea we are going to follow here also, is that I send a light signal, and I measure the time taken, and I estimate the distance, right? But things are not so simple, as I've just told you, that when light travels through space time, right, it gets affected by its curvature. And to define or to describe how one can start talking about this is where one defines a metric. So we are going to write down a metric for our universe, right? Now, as I told you, two very important
Doctor,
assumptions.
just sorry to interfere in between. This is
Sure.
the FLRW metric. Now, I was actually going through what is called the Roy-Choudhury equation, which assumes again the homogeneity and isotropy. But considering that the universe is not homogeneous or isotropic, I just wanted to ask you that are there mathematical models which assumes that universe is not homogeneous and not isotropic, and then how the equation becomes more complicated?
It will become more complicated. So there are lots of models people are working on, but as you've seen, why the standard model is so popular is that's why I said that CMB measurement of the CMB is a very remarkable observation, because it indeed establishes isotropy and homogeneity. So there are models that people are working on where you look at scales where you see small at smaller scales, you see that as we saw in the 2DF survey also, that the things are not very homogeneous and isotropic.
Mhm.
You
Right,
have regions of high density, you have regions of low density, right?
right.
So yes, there are modified gravity models, there are different kinds of models people are trying to, in fact you have to explain, to have structure, to build structure, things like galaxies, clusters, I mean planets, solar systems, galaxies, clusters. These are all structures. These are all non-uniformities over the homogeneous background, right? So if I when I talk about the FLRW metric, I am assuming that I am dealing with scales which are much larger than the scales at which these structures exist. That's why it's called the background
Background, right.
cosmology.
Yeah,
So
please
this
go
is
ahead.
the background, and you grow structures over and above it, right? So that's the idea. But yes, there are models where people work, where people do not start with the uh, assumption of isotropy and homogeneity, right? But you realize that if you include the condition for homogeneous and isotropy, is that when you can write this metric. So if you impose, so that's what I was going to say, that if I now go to general relativity, and after defining I can actually define a metric for the universe if I impose conditions of homogeneous and isotropy, which are kind of established when I look at the 2DF survey or the CMB map. Is it's not something that we cannot start with. If you impose those conditions in GR, then there is a theorem that says that you can always find globally valid coordinate system in which the metric will take this form. It's always possible is to write the metric in this form, where so this metric is what is known as the FLRW metric. In this metric, you have, if I look at the part in the bracket.
Here, sorry again to interfere. Jamshid Bashir is asking, what is metric? Please explain briefly.
Yeah, I can go back. Metric is a way which is a mathematical way of describing the geometry of the space time. That's the definition. This is how it will look like, and let me just tell you what it actually means. So if I forget about everything else, if I just look at the things in the square bracket, and even if I don't consider this term in the denominator, 1 minus k r square, I'm saying this because then, just to make things simple, you can see what do I get is dr square plus r square d theta square. This is nothing but a distance element, right? So that's what I said. We are actually trying to measure distances, right? So I'm actually trying to measure distances. So you can see what this would mean, right? If I look at dr square plus r square d theta square plus sine square d phi sine square theta d phi square, this is nothing but a line element, right? So it's like measuring. It's a way in which I can measure distances uh, in my space time, right? So this equation, the way I write it, is what one calls as a metric, is what defines the geometry of your space time, right? In this metric, this term in the bracket is what I call as the co-moving distance. There are what we call as co-moving, these are what we call as co-moving coordinates, or what we define as fundamental observers which are moving along with the expansion, because as we saw from Hubble's law, universe is expanding, right? So this is a set of coordinates. That's what we call as the co-moving coordinates. If I multiply it by this quantity, what I call as AT, then this becomes a physical distance. That is the true distance between observers. At is what I call as the scale factor, is a measure of how distance between co-moving or fundamental observers which are described by these co-moving coordinates, changes as the universe expands with time.
Okay,
T.
here I would like to again interfere. I am requesting all the viewers already. I can see 23, 24 people live. This is an excellent lecture Dr. Geetanjali is giving. And I think that it is one of the best lectures in cosmology. So we are learning from her the entire cosmology in a very brief period of time. Thank you, Dr. Geetanjali. So I have got many questions already there, Shushobon and Tech Lover, and already asking. Please hold on to the question. This is a beautiful lecture. Please listen to this because we are actually covering a complete course in cosmology. Over to you, Dr. Gitanjali.
Yeah. So what I was saying was I just told you what is AT. AT is a measure of the expansion, the rate of expansion of the universe. And this time T is the time measured by synchronized clocks by these carried by these fundamental observers. So it is like that at some time in past, all of them decided to set their clock, and then as things evolve, they measure time on the clocks that were synchronized, right? So it's the true time, it's the time that is measured by these fundamental observers. There's another unknown in this metric. What is K? If I just do simple dimensional analysis, I can see that dimensions of K would be dimensions of 1 by length square. And the quantity in physics that you come across, which has dimensions of 1 by length square, is what you call as curvature, right? It has dimensions of curvature is something which is measure of so it's like measure of curvature of slice of the three-dimensional space that we have defined, that we define using these co-moving coordinates, right? Okay, so I've explained to you what T is, I've explained to you what A is, I've explained to you what K is. What are these R theta phi? These R theta phi are coordinates a, of a fundamental observer. So if I have one fundamental observer, it will have his or her set of R theta phi. The other fundamental observer will have his own r theta phi. Now, what do I mean by co-moving is, as time progresses, these r theta and phi for the particular co-moving observer, they remain fixed. They do not change. T changes and A changes. Hence, physical distance between them changes. So you can imagine slices of three-dimensional space, each slice being described by an r theta phi fundamental observer, which remains constant as time progresses. But as time progresses, it's the scale factor A which changes, and hence the physical distance between the uh, fundamental observers changes, keeping the co-moving distance the same, right? Okay, now this one very interesting aspect of this coordinate system is, you can see, if you, those who have some background in physics would know that r theta phi are what we normally refer to as spherical polar coordinates, right? So one can ask, where is the origin of this spherical polar coordinate system that I have used? And the answer is that it really doesn't matter, right? I mean, wherever you choose the origin, the theorem in physics says that you can always redefine a set of co-moving coordinates with respect to that new origin, in which you could still write the FLRW metric in this form, right? So that's the importance of writing something like this, is what I mean, something called the FLRW metric. Okay, so this describes the geometry of my space time, right? But then that that's not all. Einstein's equations have two sides. The left hand side, so Einstein's equation reads as g mu nu. I mean, I think I. So can you confirm if you can see it? The equation is visible at the bottom.
Yes, it is visible. Capital G mu nu equals to 8 pi
8 pi
GP.
times this g on the right hand side is the gravitational constant times t mu nu. So this metric gives me the left hand side. That's the geometry, the g mu nu part. But to write the Einstein's equations, I need the right hand side, t mu nu, which is what we call as the energy momentum tensor. Right now, again, isotropy and homogeneity put strict conditions on what the form of energy momentum tensor could be. So isotropy and homogeneity require that there should be a perfect fluid that describes the matter and the energy content of the universe. That is, the components of the T mu nu should be such that T mu nu is diagonal. The components can only be the energy density rho and the pressure P. That's that's what isotropy require. That's what homogeneity requires. And isotropy requires that these components can only be function of time. Why? Because if suppose they were functions of distance, then the things would not remain isotropic. Things would depend upon in what direction I am looking at, because any particular direction as universe is expanding, if I start with something which has a spatial dependence, would change with time and I would lose isotropy. Right? So isotropy requires, so homogeneity requires that the T mu nu should be diagonal, its components should be minus rho ppp, and the fact that it's isotropic, the assumption that it's isotropic requires that both rho and p can only be functions of time. So now we are
I,
all set. Yeah.
yeah.
Yes, sir.
Also, I would like to ask you if you can. I mean, I have already explained the metric tensor, the stress energy momentum tensor. I'm not considering the Ricci and the Ricci scalar. They are actually symmetric tensor. So, if you can just briefly explain to our viewers the measurement part. I mean to say, what actually is the advantage of having a symmetric tensor?
Symmetric tensors are if I mean this is not having a symmetric tensor. It's a condition that we arrive at because we impose conditions of isotropy and homogeneity, is what leads to the fact that the tensor can take only this particular form. As I said, if I impose the condition of homogeneity, I require that this perfect fluid has to be such, I mean it has to be described by a perfect fluid, and the tensor has to have only diagonal elements, right? It can have only diagonal elements, and the diagonal elements would be minus rho ppp. And the fact that I require it to be isotropic, these diagonal elements also cannot have a spatial dependence. They can only be uh, dependent on time. And if I mean, there definitely has gone the condition for symmetry. What you're talking about, the symmetry goes into the fact that this curvature k that you see, you could actually write this in terms of Ricci scalar. You can see that this k would come out to be 6 times the Ricci scalar, where 6 is the number of symmetries that we have in the system. So yes, I mean, I thought I would not go into all that, because that would require some more intense mathematics, and I might lose. People might lose.
No,
Get
no, that
if
is
you
fine.
get too involved
Just
in
one question which
mathematics.
is coming
Yeah,
up, really
yeah.
now is asking, what if they are not diagonal?
Then it cannot describe a homogeneous space. So
Absolutely.
condition of homogeneity requires that it can have only. So if you actually start doing the mathematics and you impose the condition of homogeneity, it would require that it can have only diagonal components.
So really you
That's a
got your
requirement.
answer that if it is not diagonal, we won't get the homogeneity and isotropy, right? Please go ahead. I'm so sorry because this is so interesting and you are almost running through a course in cosmology. Thank you very much. Please.
So if I'm going too fast, you can tell me. I can slow down.
No, it
But
is
I just thought
absolutely fine.
of providing
I
a lot
think
of
we
information.
are all of us are enjoying. Yeah, a few questions are waiting. As soon as you finish, we will come to those.
Sure, sir. Sure, sure. Okay. Okay. So now we are all set. We have both the sides of our Einstein's equations. If I substitute things into Einstein, as I said, I didn't do the mathematics, but if those who are interested, we can definitely do that. But if I so suppose I've actually done this in the background, you can imagine if I do that, if I put the metric and the T mu nu form back into the Einstein's equations, I will get two equations. First equation would give me the rate of change of A in terms of you can see that I can write the rate of change of the scale factor in terms of the energy densities, energy density of the universe, and I can relate the second derivative of A with the energy density and pressure, right? And these two equations were developed by Friedmann, in the years, if I think around 1919 to 1930. That's why these are known as the Friedmann's equations
Okay,
in
may
cosmology.
I interrupt in between?
Sure, sure, sir.
Serdar Said, I think he is from Turkey. He is
Hmm.
asking, we include non-diagonal elements, then energy momentum tensor would still be symmetric, right?
Sorry, sir, I couldn't. Somehow, I think
Yeah. Can you just see the comment over there?
I don't know my screen. Just 1 minute. My
Yeah.
screen. mm, I think I'll have to.
No,
I can't
I
see.
will just remove this. Is it okay now?
Yeah, yeah. Now I can see.
Okay. So
Uh,
Serdar is asking, if we include non-diagonal elements, then energy momentum tensor would still be symmetric, right?
yeah, but it would not describe what we are looking for. Is what the condition that we are imposing is homogeneity.
Homogeneity, right?
Right. If we impose the condition of homogeneity, we can always rewrite. I mean, we can always transform. I can write my tensor in a form where it has only diagonal elements. That's what homogeneity leads to.
I
Yeah.
will just add the screen. And
Yeah.
Abhijit Kumar is asking that, is this derivation of Friedmann equation?
Well, I have not done the intermediate steps, yes, but all you need to do is you'll have to write G mu nu. You should know how to write G mu nu starting from the metric and substitute that on the left hand side of the Einstein's equation and do component wise. Ma'am, the do the write the equation component wise, and yes, indeed, you will end up getting these two equations.
Yes, please go ahead. Yeah.
Okay, so there's one thing that I did not include in my previous slides is, as I told you, Hubble constant is the value of what we call as Hubble parameter, which is a measure of expansion of the universe, is what I have denoted here by HT, and it can be related to the scale factor. Why? Because scale factor again is a measure of the expansion of the universe. So H is a quantity which is defined as A dot by A. That is time derivative of A, the scale factor, to the, so it's the ratio of the time derivative of the scale factor to the scale factor itself. So that's a new thing that has come up that I would like to point out at this point. And you can see that, so what I was saying, that if I substitute the equations into my Einstein's equations, I will get these two equations: the the time derivative, and the second order time derivative of the scale factor, which can be then related to the energy density and the pressure. Okay, so what is this rho? This rho, as I said, is nothing but the energy density, and energy density would mean what it actually contains information of what are the constituents, what are the contents of my universe, right? So as you can see, energy density gets contribution from the CDM. CDM is a short short form for what you call as cold dark matter, baryons, radiation, dark energy. I'm I mean, one should actually also write neutrinos in addition to these, but I just thought I'll keep things simple. So energy density gets contribution from all the components that constitute your universe, and similarly for pressure. So that's what I said in the beginning. I would like to now reiterate, point it out again to you. So left hand side is what? Is the dynamics of your universe, right? That is how things, by dynamics I mean how things evolve with time. I mean, how distances, why distances? Because that's what the scale factor is a measure of. So you see how things evolve with time, the dynamics of the universe. And on the right hand side, you can see it contains the content of the universe. So you can exactly see that dynamics of the universe is directly related to what the universe contains. So how the universe is going to evolve with time will depend upon what are the constituents of the universe, what all contributes to this row, right? So that leads to one more thing, that I can find solution to these equations. How? If I know how these energy densities and pressure depend upon A, right? Because if I do that, so if you imagine that I can write, if I look at the first equation here, that is the A dot by A equation, and I know how rho, this average energy density, getting contribution from all these depends upon the scale factor A, this equation would simply reduce to an ordinary differential equation, which can be solved exactly, right? And that's what now we are going to do, is to find out how these rho and these p's, they depend upon the scale factor, and hence study the dynamics of the universe. I'll come back to these parameters in some time, right? Okay, so now how do I do that? I'm not going to do a very intensive derivation here. I'm only going to give you a very heuristic argument on how one can do that. And uh, I will try to make things simple so that you can get an idea about um, how things evolve. Then difficult things can always follow after that. Okay, so you see that rho gets contribution from cold dark matter, baryon, radiation, dark energy. I'll deal with each one of them individually. That is how each one of them varies with A individually, and then we can put them together and see what happens when all of them contribute. Now let's first try to get an idea about the baryonic matter. This term, the second term, so contribution coming from matter. In fact, this matter could actually include cold dark matter and baryonic matter. Now, as I said, I'm not going to do a derivation. I'm just going to give you a heuristic argument. So you can think of that matter is like particles having some defined mass, um, some fixed number of that in, and I consider a small volume, a cubic volume, and I count what is the number of such particles in that cubic volume. That's going to give me the density, number density. And if I multiply it by mass, it's going to give me the energy density within that unit volume. Now, as we've seen that the universe is expanding, and the measure of this expansion along the length. So every length in universe expands by, as time evolves, expands by a factor at. So that means volume, which goes as length cube, would evolve as cubic power of A. Hence, if I go back and look at the number density, which goes as number upon volume, or I look at energy density, which goes as mass upon volume, you will see that it goes as a to the power minus 3. Right? So I know that how rho matter or baryonic matter and CDM will go as a to the power minus 3. Right? Similarly, I can do for radiation, that is photons. But in case of photons, there's an additional aspect, is that I know that as the universe evolves, lengths evolve. But I've also seen one more thing, that as the universe expands or evolves, the wavelengths also get stretched. How do I know that? That's what I've seen from Hubble's law, is that the things are all redshifted. So the wavelength that when it was emitted to wavelength when it is observed expands, and the expansion is measured in terms of, so it's like a length scale. It's a length scale which expands by A. So if I have a photon, the wavelength increases by A, its momentum, which goes as inverse of wavelength, would decrease as A to the power minus 1, or its energy would decrease as A to the power minus 1. So its energy density, which is energy per unit volume, energy decreases A to power minus 1, volume decreases A to power minus 3. So energy density would decrease as A to the power minus 4. So if I look at contribution, if I look at how energy density of radiation would decrease, it would decrease as A to the power minus 4. I can do the same thing for curvature. Curvature things are very simple. If I look at contribution coming only from curvature, you can see K is a constant. So energy density of curvature would go as A to the power minus 2. Now comes the most interesting part, is the last thing that contributes here is what I call as dark energy. So the most popular model of dark energy that's currently something that's actually very popular is the cosmological constant, or the lambda CDM model. Here we treat the dark energy density to remain constant through the evolution of the universe. But this, let me tell you, this is not the only model. You can have other kinds of models also, where rho de can have a scale factor dependence. But for now, we will stick to the standard model and assume that, and consider, not assume, take the energy density of dark energy to be remaining constant as things evolve with time. Okay, now once I know this, I can find solution to my Friedmann equations. And that's what we actually need to do to study what my universe looked like in the past, what is the state today, and what I can say about the future is to solve this dynamical equation. And I just told you that if I know how these rho's and these p's depend upon the scale factor, these equations reduce to ordinary differential equations, right? So now I know how rho, which gets contribution from all these, so this goes as a to the power minus 3 combined. Radiation goes as a to the power minus 4. For us, as of now, dark energy goes as a constant. If I add to it curvature, it would go as a to the power minus 2. Right? So I know how exactly this rho bar varies. If I put all of them together into this equation, it's a little complicated to discuss right now. So, what I can do to make things a little simple and give you a brief idea about how things evolve in cosmology, we can consider one component at a time. And you will realize this is not a bad idea. Why? Because this is how most of the time, this is how, as we will see, things evolve. So, if I go and substitute, so let's say if I take only contribution coming from matter, then I know that this term would go as a to the power minus 3, and I this equation would then reduce to a dot by a, that is time derivative square, equal to this constant times a to the power minus 3. I can take a square root, I get a dot by a, and then I can integrate. It's simple integration, and what I will get is that I can see that this universe will evolve in such a way that the scale factor goes as t to the power 2 by 3. That's as a function of time, it goes as t to the power 2 by 3. What does this mean? This means that all length my universe is expanding, and at is a measure of how length changes with time. As time progresses, length will increase as t to the power 3. Or I can also say, I can also make a measure of the rate of expansion. What is the rate of expansion? Rate of expansion is nothing but time derivative of a. So I can find dA by dt, which would be, I can just do the derivative. So I know the rate at which my universe is expanding, right? So I know complete dynamics of my system. I can do the same thing for every component one by one. If I do it for radiation, I will see that it will give me that scale factor expands as t to the power half. If I do it for curvature, I will see that the scale factor expands as t. What you should keep in mind is that if I look at the contribution coming from dark energy, you will see that the universe expands exponentially, right? At a exponential scale. And this is what is happening currently, because currently the universe is dark energy dominated. What do I mean by domination? That's what I mean by doing it one by one, is that each of these terms play an important role at different epochs, right? At current epoch, at current time, we see that this term is dominating over all these other terms, right? And hence, our universe is expanding at an accelerated rate. That's why when we see an accelerated expansion, we say that we require something like dark energy. I'll come to that in some time, right? Okay, so I know what the evolution of my universe would be with time. I can also understand this evolution in terms of what we call as, this is just doing some mathematics, just rewriting equations in terms of new parameters, some dimensionless parameters, what I call as the dimensionless densities, energy densities, I denoted by omega. And if I continue, just rewrite the equation, solve them in terms of omega, I can see that there can be situations where my universe, I mean, so these are possible solutions that I will have. So these are not the only solutions, these are possible solutions. All this is equally, all this is possible, right? When I put these conditions into my Friedmann equations, is that I can have a situation where a universe would expand, turn around, collapse. So what people sometimes call as the big crunch. So you'll have, it collapses. So these universes are called closed universe. So closed universe is a possible solution to the Friedmann equation, right? You can see that would happen if matter would the contribution from matter would be much much greater than the contribution from curvature, and we are ignoring contribution from dark energy and radiation, which is not true because currently dark energy is a dominating component. Then you can also have a situation where my universe would expand always, what we call as open universes, or there could be a intermediate situation to two of them, what we call as flat universes, where this turnaround time would be at very large time, it's an infinite. Okay, so I have kind of established a basic framework, studied the dynamics, kind of build a framework that explains the dynamics of the universe, and I can summarize it in form of this graph. So this graph is nothing, if you look at it carefully, it's a plot of the energy densities as a function of scale factor. This is the right edge of the graph is today, where we are today, the present time, where we choose the value of the scale factor to be 1. And as we go to the left is when we are in the past. So you can see in past, so these lines are basically contributions of energy density coming from various different parts, like dark energy, radiation, matter. So you can see in past we had a situation where radiation dominated, then the universe became dominated by matter, and this is where we are currently. If you look at this graph carefully, at current situation, current epoch, it's the dark energy which is dominating. Another way to summarize what we've just studied is this famous pie charts that you must have seen. This is what we call as the energy budget. Energy budget is nothing but contribution to energy density coming from different uh, constituents of my universe. So this is today, but this is roughly 13 billion years in the past. So you can see in the past it was dark matter and baryon dominated, and today the domination, I mean, most almost 70%, 68% of the energy density contribution comes from dark energy. Roughly 26-27% is dark matter, and only this is the small 4% is what is baryonic matter, of which you and me are made up of. Rest is what you call as dark matter, and dark energy are the darkest secrets of cosmology. And that's what my remaining talk is going to be about. So this is where we are today. So where we are today? Today we are at a point where majority of the contribution, 96, I mean roughly, as you've just seen, 96% of contribution to our energy budget is coming from two components which we have no idea about. That's why we call them dark matter and dark energy, right? Now how do I know that I need something like this? That's what I just said, that why do we say the standard model is so popular, which requires dark energy? Everything comes from observations. We know this from observations only, is that we require something like dark energy. If one, I mean, there are very important observations in cosmology or astronomy. We measure the light curves, we observe the light curves of supernova 1a. Supernova 1a are what we call as standard candles in cosmology. Standard candles are just like, I mean, as the name suggests, are objects which have standard luminosities. So you know how much, what is their luminosity, and if you measure the flux that you collect because of them, you can estimate distance to them. So they are called standard candles. They are very important in cosmology. So when we look at light curves of supernova 1a, these light curves are an evidence of the fact. So these were the first set of evidence that told us that the universe is expanding, and not only expanding but expanding at an accelerated rate. What does this mean? That the rate of expansion is also, so one, universe is expanding, its size is increasing, and the rate at which this is increasing is also an increasing function of time. That's what we call as accelerated expansion. So hence we require something. Why? Because if otherwise I look at everything that is being held together in, when we talk of cosmology, when we talk of structures, is gravity. But gravity is an attractive force. So hence we need something that exerts a negative pressure, a repulsive pressure, which opposes or behaves in an opposite way to gravity, as gravity, so that it can overcome it and we can have an accelerated expansion, right? So there are other observations also now in addition to supernova 1a. People have observed what we call as baryon acoustic oscillations and gravitational lensing and clusters of galaxies. All these observations tell us that there is something exotic, right? That we still don't know what it is, what is its nature, but there is something exotic which has a negative pressure. The simplest example, and hence that's what leads to the standard model or the lambda CDM model, simplest yet probably something that can explain all observations mostly today, that's why it's very popular, is that is a model where we have the dark energy density to be constant and pressure equal to minus rho, right? This is a cosmological constant which was first introduced by Einstein himself, right? And now we see that it is indeed something that can explain the accelerated expansion. But this is, as I said in the beginning also, this is the popular model. Why popular? Because whatever we see, the observations, it has been able to explain it. So unless you find something which is not being explained by lambda CDM, is that you would challenge. I mean, you would believe that it's not true. But that doesn't mean that it's the only model that's existing. There are other models also where energy densities are functions of time. They have complicated dependencies on times. These are different models by the which go by the name quintessence, phantom models, Kessens model, tachyons. There are lots of them, not only different dark energy models. As I when sir initially asked, I also said people have also worked with modified gravity models where people don't not only. So if I look at what do I mean by different energy dark energy density models, if I go back to Einstein's equation, so by looking at modifying dark energy models, you are actually modifying the right hand side of the Einstein's equation. That is, you are playing with the energy momentum tensor, uh, the constituent of the universe. But then you know that dynamics of the universe also depends upon its its geometry. So there are models where people play with geometry part of it also, which are known as modified gravity models. There are lots of modified gravity models also which people have tried to explain the accelerated expansion also. So there's that's where the need of dark energy comes in. Then the other exotic part is the dark matter part, which again requirement arises from observations. It is believed to be non-baryonic because the way it interacts, it only shows gravitational interaction, doesn't show any kind of electromagnetic interaction. That's why it is called dark, right? And it has been observed indirectly. Nothing, no detections have been made in the lab. The first time it was observed was by Zwicky in 1933, where he was actually measuring velocities of galaxies in chroma cluster. Now you also see that evidence in rotation curves of galaxies. So if you look at rotation curves of galaxies, you see that you have flat rotation curves. So, but what you expect from simple theory is that rotation curves should be, I mean, the velocity should decline as you go away, farther away from the center of gravity. But you see that after a point, velocity remains constant, which requires much more matter than what is actually observed in galaxies, in the halos of the galaxy. And because we can't see it, we call it dark matter, right? And it is called cold because it is believed to be non-relativistic, right? So these are two exotic components that one talks of in standard model. So as I said, standard model is probably one of the most popular acceptable model, but it also suffers from two very serious problems. I'm not going into go into details of flatness and horizon problem because this requires general relativity and solution. But these are two very important problems. Something, particularly the horizon problem, is something that really requires attention. And this is where people bring in inflation in cosmology, is to resolve the flatness and the horizon problem, right? So people believe that at so what is inflation? At very early ages, at very early epochs of time, people require to solve the horizon problem a very rapid expansion of the universe, almost 60 e-fold expansions to what it is at an initial stage. And this rapid expansion phase is what people call as the inflation, where the universe suddenly exponentially expands. And we've seen that there is a possibility one can actually have exponential expansion if we have something like dark energy dominance. So there are scalar fields that people use there to describe the inflation, and this normally occurs at very early stages of the universe, that is some 10 raised to the minus 32 seconds after the big bang. Just to give you an idea, you saw that it was only after a few millions of years where the stars were formed, millions of years. And here we are talking about 10 raised to the minus 32 seconds. So this is that part of that phase of universe where we still lack a lot of understanding, right? But yes, this is where people often talk about inflation, is to solve these two very important issues that arise with the standard model of cosmology, right? And yeah, so as you see, uh, we've talked about dynamics, we've talked about evolution, we've talked about contents of the universe, and you see that everything that we talk about is so dependent on observations, right? So cosmology has now indeed become an observation driven science. So what we talk of, the theories that we make, are all dependent upon what we observe. It's completely an observation dependent science, and that's why there's a whole lot of investment that is currently being made to improve the kind of observations we are making, and has led to these very expensive, large scale observatories, both ground based and space based observatories in recent past. All of you have, so I've just listed few of them. uh, One of the very famous, everybody now knows of it, has been talking about it, is the James Webb Telescope. This telescope has been designed to work in infrared astronomy, right? it is it has got immense resolution and sensitivity. I mean, it's a huge improvement over the Hubble Space Telescope. Then we have the Euclid, which is going to be a near infrared, it's a near infrared telescope. So you can see that we are trying to observe universe in different wavelengths. It's because different phenomena show up, signatures show up at different wavelengths. And we have the extremely large telescope coming up. This is again infrared. It's going to be a huge investment that's going to come up uh, to observe the universe in infrared. Then we have the DKIST, which is in Hawaii. Is again, it's a telescope that's completely dedicated to observing sun. Sun is something which is closest to us in terms of the distance scales we started with, and there is yet so much we don't know about our sun. So this is a complete dedication to sun. Then we have the SKs coming up. Part of SK is in South Africa, part of SK is in Australia. It's a it works in the radio range, and it's going to be a complete game changer. Let me tell you, radio astronomy is something which is going to completely change the way we look at things in astronomy, astrophysics, and cosmology. And then we have the Rubin Observatory, definitely, which is in Chile again, which is the legacy survey. It's going to be very important for measurements of dark energy and dark matter. It's going to be making measurements of transient phenomena, and looking at measurements of dark energy and dark matter, right? So I think we can probably kind of had a review of what we observe, how in past such observations led to the study of dynamics, how different models are built up, how by looking at the content, playing with the content of the universe, one can study different dynamical models, and how do we actually make such observations using these telescopes, right? So I think I can end here in terms of my presentation and talking, and then go ahead, see if I can answer a few questions, something
Absolutely.
that I know of.
Thank you very much. It was, I think I have to, remake my thumbnail as not a talk with Dr. Geetanjali Sethi, but rather a complete course on cosmology for about an
Thank
hour.
you so
It is really wonderful. I mean to say, this is something really great. Okay, I will just come back. I know I have taken a lot of time. Just some quick questions. Pawan
Sure.
Gaonkar's question, I think, Professor, you have already answered how much general theory of relativity plays. Then we have got a question from Rohit Gupta. He is asking that, do we ever break large-scale homogeneity and isotropy?
There are models people are working on, not large scale, particularly. There's a very important thing that goes into cosmology is where we have averaged, we apply Einstein's equations on an average scale. That's more interesting to look at. But you see that matter is not distributed. So if I go back to smaller scales, I see that there is a lack of indeed homogeneity and isotropy. So there are models where people believe that we cannot apply homogeneity and isotropy, and hence Einstein's equations the way we are at very large scales, right? Because at large scales, you don't have the same kind of format as we have at small scales. You have matter only existing at small scales, and at large scales, it's mostly empty, right? So, yes, indeed, there are different kinds of models people are working with, right? And on an average, people say this is an important problem in cosmology. In fact, what we call as the averaging problem in
Averaging problem,
cosmology.
right?
Yeah.
Rudrasi has got a question. Will it ever move away from us at greater speed than light? I think we have no model right now
That's
about
yeah,
it.
yeah.
Yeah. Okay. Rayleigh now is asking, ma'am, what are the drawbacks of Einstein field equation?
Well, I mean, that's not how we normally attack problems in physics. We don't say that there are drawbacks of Einstein's field equation. What more logical would be to ask what are the limitations of Einstein's field equations? Are there places where Einstein's field equations break down or things like that? One cannot say that there are any drawbacks of Einstein's field
Yeah,
equations. It's how
absolutely.
we apply them.
Yes. Uh, Shushobhan Chattopadhyay is asking, has the Copernican principle tested?
Well, as I said, CMB, and I mean, if I look at the CMB, uh, isotropy is what you can see. Homogeneity and isotropy is what you see from all these measurements. So I think that's a way to test that indeed you have a global isotropy, if you say tested in that sense. Right? Yeah.
Right. Tech Lover is asking, what was the turning point which led Einstein to formulate theory of relativity?
I don't know. I mean, I don't know what was going on his mind. I mean, probably he was, it was already looking at the observations were already there. People were indeed looking at expanding universes, and there was this steady. I mean, he initially actually brought in the cosmological constant to, or got rid of the cosmological constant. In fact, there's a lot of argument that he had with Friedman and people who were looking at expanding universes at that point of time. I don't know what was
I think I
in
was
his
going
mind.
through a book just to share with you, Professor, is that if you consider special theory of relativity, definitely how the Maxwell's equations would behave with the speed of light. And if
Yeah.
it is general theory of relativity, it was the equivalence principle that while he was sitting at the Zurich office, suddenly he thought that if the floor collapses and if I'm falling down, then I won't feel that weight. I think that actually led to the turning point of his,
Okay.
creation.
Yeah, I mean, yes, I mean, I was just thinking in terms of probably cosmology. Yeah, true.
Okay,
Yes.
yes. Abhijit Kumar has got a question. Ma'am, we consider universe is isotropic liquid, but in quantum mechanics, it is field. So how can we relate both of it? How Hawking derivation is derived?
Well, I would not like. I mean, I would not be capable of commenting on Hawking radiation or Hawking derivation. But when it comes to talking about field is not a quantum mechanical concept. Field is a concept that exists even in classical physics.
From
Field
mechanics, right?
is field is just a way to describe action at a distance, right? When we talk about how things are related, when something happens here and how it will affect something at a distance is where you bring in the idea of field. So I
Right.
would not say that field is something which is limited to an idea concept that's limited to quantum mechanics.
Absolutely,
Yeah.
absolutely. And I told in a few of my videos that when people think of quantum field theory, etc., field is something which is called classical field. Even in gravity, electromagnetism, everywhere there is field. So this is nothing new, rightly told. Shushoban is telling that I thought neutrinos behave like radiation before decoupling and presently after decoupling as matter. Can you please elaborate why we should include neutrinos separately in Friedmann equations?
No, I mean, it's not that they behave like radiation or they behave like matter. I mean, they do have mass. So their behavior, now we know that neutrinos have mass. It's from observations we know. So they have their own kind of behavior. In fact, neutrinos play a very important role at the time of structure formation. In structure formations, the structures that we see today, we could not explain if we do not include neutrinos. I just
Neutrinos,
didn't include it because I wanted to keep it simple, right? But
right.
yes, I mean, what we see today, structures are very important that can be explained using neutrinos.
Okay, one of my subscriber from New York is telling, hello and thanks, excellent talk.
Thank you,
Okay,
sir.
and Seder is asking, could string theories which have tachyons built in the theory be a candidate for dark matter or dark energy?
People have been working with tachyonic. I don't have idea about string theory. I mean, I don't have that background, so it will be difficult for me to comment. But yes, people are working with tachyons. Tachyons are possible candidates when we work with different dark energy models.
Right. Nadeem Iqbal is asking, space is expanding and the fabric of space does not rip apart. If we stretch any material, it has a breaking point. But what material is space made of it? It keeps on stretching and never rips apart.
So it's not something like physical that you think of, right? You
Yes,
can't think of it as a physical material, right? It's like the space time itself, the geometry that we talk about, right?
right. Abhijit is asking, ma'am, I have done research on general relativity. I have shown that one curvature create more curvature around it, energy momentum tensor acquiring mass from field.
It's interesting, right? I mean, good. I mean, we would like to know more about it.
Yes,
It would be
absolutely.
nice to hear from him.
So these are the questions that we have. And thank you, Professor Geetanjali, for
Thank you.
almost giving a complete course on cosmology. And actually, you made it so simple, both the mathematics part and the observations and the presentation is, I mean to say, this is really wonderful. Okay, a few more questions, one thing coming up. Yeah, so someone is asking, you told dark matter is only gravitational interaction. Can it can it have very small couplings with the standard model of particle physics?
Definitely, it can. I mean, it seems to have very very weak interactions, so weak that we've not been able to detect them yet in the lab, right? But we cannot rule out anything. Something probably that requires little more lot more work than what we've already put in, right? Yeah.
Okay. He
Yeah,
is
we'll
asking that what are some reliable observations for constraining inflationary models? Also before BBN, are there any observations?
before the Big Bang nucleosynthesis, well, that area, very early part of the area is indeed, well, I would not say immediately before BBN. Yes, that still has, we've got a good knowledge of epochs before BBN from particle physics. The knowledge, we do have knowledge of that. And the so but very very early epochs is what we are talking about, where we talk about quantum fluctuations and all, is the areas where we still don't know much about, right? We don't have much idea about.
Right. And Mohammed Hamza is asking, ma'am, is there any research going on gravitation? I mean to say this
Well,
very general question.
yeah,
Yes,
there's a lot
difficult
of
to
work
answer.
people are doing. Cosmology is a very growing field. It's still a very growing field because of the observations, new observations that are coming in. There's a lot of work that's going on.
Last question to you. I know, I mean to say, maybe this is, he's asking, is there any research going on in graviton?
Oh, people are working on various things. There are people working on such particles that can have that we can, if we look at describing the gravitation associated with gravity. Yeah,
Yep.
I mean, I don't work in that area.
Yeah. Teklever is asking why Einstein field equations not predict something before Big Bang. Is the Big Bang singularity is the limitation of GR?
Well, it's a limitation of GR in the sense it's GR is a classical theory, right, which works at classical. So every theory has a length scale, an energy scale associated with it. The scales at which general relativity or classical theory works are very different from scales that we have at initial, the quantum scales, right? So uh, you don't get you don't require things like that. So it's just like when you start studying physics, the first thing that you study is the ratio of scales of electromagnetic theory and gravitational field, the scales at which gravitation becomes important and electromagnetic interactions become very different. So in the same way, um, those are energy scales where we are still not able to see how gravity would behave.
Okay, we have got another question from Soham Oja. What is Boltzmann brain on universe and its effects?
I'm not aware of something of that kind.
Yeah. So my last question to you, Professor, would be now, as we go into the theory of everything kind of a approach. So one thing is that we already have got general theory of relativity, which is taking care of the, I mean to say, the large scale universe and cosmology part. We already have got the quantum field theory, which has united special relativity, quantum mechanics, and quantum electrodynamics. So, as of now, we have got these two theories which are experimentally proved. But string theory or graviton is something which is on the lookout. That means we are not yet find out any theory which is uniting gravity. We are keeping apart gravity.
True,
Only general relativity and cosmology takes into account the gravity, but it again does not take into account the quantum mechanics part.
true,
Now,
true.
this is just a general curiosity to ask you. The work of Stephen Hawking, or whatever he has done, that is basically trying to unite the very big general relativity with the very small quantum mechanics. Is that so?
Well, so I would, as I said, it's not a, he's worked on there are lots of things
Yeah.
that he has come up with. Yeah,
Right.
but definitely, I would not like to
Okay,
say
comment on that.
it's not,
Sure, sure,
yeah,
no
it's
problem.
not something that my knowledge is about. Yeah.
Okay. Since all things arise from Big Bang, mass and charge, mass and energy relation has been already proved. Is there something which could predict the relation between charge and energy?
Yeah, we know how, we know the energy carried by an electric field or a magnetic field. We already know that if you have a electric field, it would definitely has, you'll have to do some work to set up that electric field. I think
Right.
that's what you mean by looking at energy associated with
I
charges
think
or
that is
parts.
classical
Yeah,
electromagnetism that
yeah.
actually defines this. Right.
Yes.
Okay, so I won't take much of your time. So again, a heartfelt thank from me, from the
Thank you
entire
so much.
subscribers, and it has
Thank
been
you.
a wonderful talk. I think that this talk is going to be remembered as a special day, 30th of June, when special relativity was born, and you have given a great talk, an entire journey, starting from the basic level to cosmology. I mean to say, this is what it is saying. Mohammad Hamza is telling, ma'am, why every time Big Bang is shown and the universe expansion is shown, why a kind of three-dimensional balloon? Oh, he's asking that why do we give an analogy with a balloon?
That's what we understand by just to kind of somehow depict the expansion of the universe from in terms of scales, length scales, like what we talked of, the expanding universe. That's why that's
Right.
the
I
reason.
think that if we draw small circles on a balloon and then if we blow up, we can
Yeah,
see how
things would,
the
that would be a
distance
three-dimensional depiction. Things are very
dimension.
different because right now it's what we deal with is a four-dimensional space-time.
Four-dimensional, right,
Yeah.
right. Ronaldo Jones is telling great lecture. Tech Level is telling thank you, Professor Shonak and Professor Geetanjali on this very great talk. Heartily thanks for this. So thank you, Professor. Thank you. Thanks a lot for
Thank you
this
so much, sir.
because
Thank you.
this is it has been a great lecture, and we wish you to take you back again. I mean to say, taking you back. I know you are quite busy, but It is not only one podcast which is enough with your great knowledge and amazing presentation, very lucid explanation of very difficult mathematical equations, especially general relativity. I'm sure that all the viewers right on the screen, I can see 22, and more will be viewed in this podcast because it is recorded live. So that's phenomenal. Thank you for this. It is a
My
historic
pleasure.
day for me, a very important day for all the physics lovers, 30th of June 1915, and today is 30th of June 2024. Amazing talk with you, Dr. Geetanjali. Thanks a lot. It has been
My
great.
pleasure, sir. My pleasure. Thank you so much, sir. Thank you.
Any last minute message that you want to give to the young people who wants to come into cosmology?
I I just sincerely hope that I've motivated some of them to go study general relativity and cosmology. That's always the idea of a teacher, and I feel as a teacher I should be able to motivate them. I hope I have been able to do the same.
And St. Stephen's College is blessed to get a professor like you. I am feeling
Anytime,
so
sir. Thank you
jealous
so
with
much,
your
sir.
students that
Yes,
each
sir.
time that
Yes,
they
sir.
get a great explanation from you. St.
Thank you
Stephen's
so
College.
much, sir. Thank you.
Absolutely.
Thank you, sir. Thank you.
Thank you. Thank you. Goodbye. Take care.
Goodbye, sir. Thank you.
Bye.